Okay, today you're just you and me, and we are going to solve some questions about maximum and prime ideal. Okay, do you have any questions about video lectures? Do you think that these recitation hours is useful for you? Okay, you think it is quite good for you, but you're following a little bit behind of the lectures. Okay, if you have any questions, please interrupt me and ask your questions. Okay, this is something like a private lesson. Okay. Okay, now our first question is let R be the ring of all continuous functions on the interval, close the interval, 0, 2. And let I be the subset of R defined by I containing all functions in R such that f of 1 is equal to 0. Okay, then we are going to prove that I is a maximal ideal of R. Yes. And then we are going to determine the quotient ring R over I. Okay. Do you have any thoughts? Any suggestion? No? Okay. Now first, to show that I is a maximal ideal of R, first we need to show that I is an ideal. Then we are going to show that it is maximal, but we are going to do it by just defining a homomorphism from R to somewhere else. Okay, so let us define phi from our ring of continuous functions on 0, 2 to the real numbers, taking a function f of x to its value on 1. Okay, and it's your job to check that phi is a homomorphism. Okay, now after showing that this is a homomorphism, if we look at its kernel phi here, consisting of all f of x in R, such that the additive identity of R is 0. So the function taking all values of x to 0. Okay, for all x in 0, 2. Okay, so actually this means that sorry, the image of f of x is f of 1. Okay, sorry, the image of f of x is, I had to do in this way, phi of f of x is equal to 0. Yes, so this is nothing but containing all f of x in R such that the image of f of x is just the evaluation of function f at 1. This is f of 1 is equal to 0. And this is nothing but the definition of our ideal I, which is containing f of x in R whose image, yeah, Ahmed, you're right. The image of 1 is equal to 0. So if you look at the kernel, this is nothing but just I. Okay? So after showing that phi is the homomorphism, kernel phi is found to be the given subset I. So this implies that as kernel is an ideal, I is an ideal of R. Okay. Now, how to show that I is a maximal ideal? As you know, if you have a commutative ring, let me call S a commutative ring with 1 and J a maximal ideal, then the quotient ring of S with respect to the maximal ideal J becomes a field, right? So this is actually an if and only if statement. So in this case, actually, if we can show that this homomorphism phi is actually surjective, then we can use first isomorphism theorem. So let us first show that phi is onto. Phi is onto. So let us take, let R be an arbitrary real number. Then we have to find function in our ring of continuous functions on 0, 2, whose images are. So let us consider the constant function. F of x is equal to R. Okay, then what we have is that phi of f of x is equal to R, and this gives the surjective property of our function phi. Okay, so phi is onto, so apply first isomorphism theorem. What we have is that R over kernel phi is isomorphic to the field of real numbers, and we know that kernel phi is equal to I. So R over I is isomorphic to R, which is a field, and hence, since the quotient of R with an ideal gives an isomorphism to a field, this means that I is a maximal ideal. Okay? Any question? Problem? Yo, okay. Then let us continue with our second question. Second one. Let's consider the ring. Consider the ring Z something like this, Z root 10, which contains all elements of the form A plus B root 10, where the coefficients A, B are coming from the integers, okay? And a subset of it, of Z root 10, defined by, let us call it P, and this is generated by 2n root 10, which is given as A plus B root 10, such that A, B are integers and 2 divides A. Okay, so the coefficients of this term, this A, are even. Okay, so our aim now is to determine the quotient ring Z root 10 over P, and also we have questions, is P a prime ideal? And the other question is that, is it maximal? Okay, now I'm going to show the primes of P by direct computation. Okay, but at the end of the question, we are going to use some homomorphism. A homomorphism, while we're showing that is maximal, but you can do it first, the maximality, and after that, you can say that every maximal ideal is prime, so P is prime, but I'm going to keep the order here. Now, first, I'm going to first show primeness. Suppose that A plus B root 10 and C plus D root 10 are elements of Z root 10 such that the product of these two times C plus D root 10 lies in our ideal P. Okay, what was the definition of a prime ideal? Recall, let me write. If we say that P is a prime ideal, P is a prime ideal if X times Y is in P, implies that either X in P or Y in P. Okay, now for our question, if we take these two elements whose product is in P, then we need to show that one of them lies in P. Okay, then let us apply the product here. A plus B root 10 times C plus D root 10. The product here, if you apply it and make suitable parentheses, then you will have AC plus 10BD plus, in root 10 parentheses, AD plus BC root 10. This is in P. Okay. Now, if you remember, in the ideal P, we have no condition on this coefficient B, but the other coefficient without root 10 has to be an even number. Okay. So now this means that since this product lies in P, then it's only necessary that this is in Z and this is in 2Z. Okay. And this is in 2Z. We have no problem with AD plus BC being in Z. So we have to consider AC plus 10BD. AC plus 10BD in 2Z is an even number, means that since this is even, A times C is even, and we cannot have that the product of two odd numbers is an even number. So this means that either A or C is an even number. But this makes us the conclusion that A plus B root 10 in P or C plus D root 10 in P. So we have started with two elements whose product lies in P, and at the end we have shown that one of them has to be in P, and hence P is a prime ideal. Okay. Now, for maximality, let us define. Okay. For maximality, let us define phi from our ring z root 10 to 2z. No, z over 2z, z2. Okay, and taking a plus b root 10 to the modular class of this coefficient a. Okay, modular class of a with respect to 2. Okay, then check that phi is a homomorphism, and clearly it is surjective because we have only 2 elements in 2z. We have, yeah. No, it is surjective. Is it surjective? Is it surjective? Yeah, it is surjective. Of course, we have even and odd coefficients for a. So for even coefficients, we have 0. For odd coefficients, we have 1. So it is onto. Yes. So let us check its kernel. Kernel phi. I think it is not hard for you to check that a function is a homomorphism, is a ring homomorphism. So I leave it to you as an exercise. You need to check that our function preserves addition and it also preserves multiplication. So let us check its kernel. It contains all a plus b root 10 in z root 10 such that the image of this one, phi plus b root 10, is equal to, no, where is my pen? My pen is broken. I'm sorry. It just gone. Okay. Let us. My tablet died, so let us continue in 5 minutes. No, it's okay. It's back. Just a minute. Yeah, here. Okay. Can you? Here. Can you see the screen? Or should I stop and reshare? Okay. Okay, this is onto kernel phi. Okay. Now kernel phi contains a plus b root 10 in z root 10 such that the image of this one, b root 10, is equal to the modular class of 0. So this means that, okay, for me, let me stop and reshare. Share screen. No, I have something wrong with the C. Stop sharing. Okay, now I'm going to do it again. Yeah. Yeah. Okay, with my device. Weird. Okay, I'm connecting. I'm sorry for this technical issue. Yeah, here I'm going to share it again. Yay. Let me also enable chat. Okay. Now this means that a plus b root 10 in Z root 10 in our ring, what was the image of this A plus B root 10? This is just the modular class of A. This is equal to 0 bar. And this means that A plus B root 10 in Z root 10 such that A is congruent to 0 modulo 2 means that A is an even number. Or we just write 2 divides A. And this is nothing but the definition of our ideal P. Here, our ideal P here. So this means that our kernel is P. Okay? So we have a surjective homomorphism with kernel P. This means that by first isomorphism theorem, Z root 10 over kernel phi is isomorphic to Z over 2Z, which is Z root 10 over P is isomorphic to Z over 2Z. And we know that Z over 2Z is a field. And this quotient, Z root 10 over P, is isomorphic to this one. And so P has to be a maximal ideal. Okay? So actually with this one, we also determine the quotient ring Z root 10 over P. It is isomorphic to 2Z, Z2, and P is a maximal ideal. Here we have seen an example of a prime ideal, which is also maximal, but this is not always the case. We know that every maximal ideal is prime, but we are not sure that not everywhere every prime ideal is maximal. Okay? Do you have any questions? Any problem? No? Okay. Now let F from R to R prime be a ring homomorphism. Yay. And let P be a prime ideal of R prime. Now our aim is to show that the preimage of a prime ideal is also prime in the domain ring, and prove that F inverse of P is a prime ideal of R. Okay? Now, do you remember that the preimage of an ideal under a homomorphism is an ideal in the domain ring? We have shown that. We have shown that F inverse P is an ideal of R. In some recitation notes, I don't remember. So we just need to show that the preimage of a prime ideal is prime, okay? So aim is to show that F inverse of P is prime. So we are going to take two elements such that the product of these two lies in this ideal, and we are going to show that one of them has to lie in this ideal. Okay? Now suppose that suppose that A times B is an F inverse of P for AB in R, then show that A in F inverse of P or P, just one of them is enough by definition, or B is an F inverse of P. Okay? Now, A times B is an F inverse of P implies that actually the image of A times B lies in the idea P. FAB lies in P. Okay? Now, use the fact that F is a homomorphism, as F is a homomorphism. Okay. Oh, okay. As F is a homomorphism, then what we know is that we can write F of A times B as F of A times F of B, and this is in P. Now, use the fact that P is a prime ideal. Since we have a product inside P, one of the elements must lie in P. As P is a prime ideal, here from this product, F of A in P or F of B in P. Okay? And from this one, we have A in F inverse of P or B in F inverse of P. Okay? So we have started with A times B is an F inverse of P, and at the end we have reached that A in F inverse of P or B in F inverse of P, which implies that F inverse of P is a prime ideal. Okay? So the preimages of prime ideals under homomorphism are prime. Any problem? What about the images? If the question is that is the image of a prime ideal always prime? Do you have any counterexample, or do you have any comment on this? Is it always true? We know that the preimages of prime ideals are prime, but what about the image? The image of a prime ideal is prime or not? It is not always the case. So consider no. Our answer is no. So let us consider phi from Z to Z10 or Z over 10Z. Okay? Taking any integer to its modular class. Okay? Equivalence class. So now consider 0. 0 is a prime ideal. The ideal generated by 0 is a prime ideal in Z because Z has no zero divisors, as Z has no zero divisors. What does it mean? If you have A times B is equal to 0, this means that either A is equal to 0 or B is equal to 0 in Z, right? It is also shown in one of the lecture notes. Okay, now 0 is the prime ideal in the domain. So if you consider the image of the ideal, the image of this ideal, phi of P, then this is nothing but the ideal generated by the modular class of 0, right? Okay. But here in Z over 10Z, we have 0 divisors. Okay. But the ideal generated by the modular class of 0 is not prime in z over 10z. For this one, since take since 2 times 5, for example, is equal to 0, but neither 2 nor 5 is equal to 0, okay? Because, or you can write, because z over 10z has 0 divisors. So in the first part, we have shown that the preimage of a prime ideal is prime, right here, but it is not always the case that the image of a prime ideal is prime. Okay? Question? No? Okay, let me continue with my actually last question for today. Okay, it is going to be a short lecture. Our fourth question. Now let R be a commutative ring with 1. Commutative ring with 1, with multiplicative identity, I mean. Suppose that P is a prime ideal of R, containing no 0 divisors. No 0 divisors. Now, our aim actually is to show that in this case, under this condition, R has to be an integral domain. Prove that R is an integral domain. Okay? It's an interesting condition. And under this, R becomes an integral domain. Now, let us suppose that we only need to show that R contains no 0 divisors. Okay? Now, suppose that A times B is equal to 0 for AB in R. Now, at the end, we are going to show that A or B is equal to 0. Our aim is to show that A is equal to 0 or B is equal to 0. Okay? Now, we know that since P is a prime ideal, it's an ideal, right? As P is an ideal, we know that it contains 0, the additive identity. 0 lies in P. And this means that, and so A times B, which is equal to 0, lies in P. Now we have a product here, A times B lying in a prime ideal. This means that either A is in P or B is in P. Since P is a prime ideal, here we have the product, so A is in P or B is in P. Now, what was our aim? Well, our aim was to show that either A is equal to 0 or B is equal to 0. Now, okay, without loss of generality, we may assume that one of them lies in P. Without loss of generality, assume that A is in P. Okay? Now, if A is equal to 0, then we are done. because our aim was to show that one of them is equal to 0. We are done. So assume that a is not equal to 0. So assume that a is different from 0. Okay? Now, in this case, we need to show that b is equal to 0. Okay. Now, here, what was our assumption? Our assumption was that P is a prime ideal of R containing no zero divisors. Okay? Since P does not contain any zero divisors, this means that since A times B is equal to 0 lying in P, B has to be equal to 0. Okay? Otherwise, let us explain this one. Otherwise, AB is equal to 0 and B is different from 0 means that A is a zero divisor or B is a zero divisor. Because here, in this case, we have assumed that A is different from 0. So if B is different from 0 also, this means that A and B are zero divisors in P, but our condition says that P does not contain any zero divisors, okay? So in this case, we have found that B is equal to 0. So in either case, we, at the end, we reach the conclusion that A is equal to 0 or B is equal to 0. Therefore, in any case, A is equal to 0 or B is equal to 0. Thus, R contains no zero divisors and R is an integral domain. Okay? So if you have a prime ideal containing no zero divisors in a commutative ring with identity, then that commutative ring with identity has to be an integral domain, that it contains no zero divisors. Okay? Now, this was my last question. Do you have any questions about the lectures? About the subjects that are covered in recitation or online video lectures by Mustafa Korkmaz? Do you have anything to ask? No questions? No? Okay, then this is all for today. Okay, if you have any questions, you can write it on forum or Notki class, Medu class, or you can send an email to your instructor or to me. In any time, we can arrange a Zoom meeting to ask your questions, okay? In private, or some other people may be included. Okay, thank you for today. Okay, hope to see you next week. See you. Stay healthy, okay? Wash your hands.